Let's solve question 6 from the midterm 2 practice packet that Bob Johnson put together. So the scenario is that we have a magnetic field, a uniform magnetic field, magnitude 0.35 Tesla, pointing into the page. That's all the purple X's. And then we have a particle whose mass is the same as the proton mass, 1.67 10 to the minus 27 kilograms. The magnitude of its charge is the same as an electron or proton charge, 1.6 10 to the minus 19 coulombs. We don't know whether it's plus or minus yet. And it's moving in a circle with speed 3.2 times 10 to the 6th meters per second. So there it is, going around a circular orbit of radius capital R. So the first thing we want to determine is what is the radius of the circle and what is the sign of the charge. Is it positive or negative? So let's pick some point on the orbit and see which way the magnetic force would point on it. Let's pick this point. So here we go. I'll pick the kind of the bottom of the orbit here. So then this is my velocity vector. Let's assume that the charge is positive. So we have F magnetic is Q V cross B. Okay. Now this looks like my left hand in the video, but it's really my right hand. So we're going to get the correct answers. So I'm going to say V, I have to point my thumb down. You see I go V cross B because B is into the page. So here's V cross B. If I do V cross B, so V is to the left, B is into the page, the result would be that the force points outward away from the center of the circle if I had positive Q. If I have minus Q, then of course I just flip the direction. So it appears that we must have Q is less than 0 because it seems like V cross B by itself points outward, like radially outward. So therefore, Q V cross B, therefore Q V cross B points radially inward, which is what we want. We want a centripetal force toward the center to keep it going in that circular orbit. Okay, so Q must be negative. And then, what is the force keeping this thing moving in a circle? It's the magnetic force. So we can say mv squared over r. That is like whatever force is needed to keep it going in a circle of radius r at speed v. And that must be the magnitude of the magnetic force. So that must be the magnitude of Q V cross B. And, V is in this plane of the board, and B is perpendicular to the plane of the board. So these vectors are perpendicular, so the magnitude of this cross product is just V times B because they're already perpendicular. So this is just the magnitude of the charge times the speed times the magnetic force. So then we can solve for R. So that gives us that the radius, okay, so radius is going to go over here, so then this stuff comes down, so we have mv squared divided by q v b, and we can cancel one factor of v. So that gives us mv divided by magnitude of q times b. Okay, I guess we could plug in numbers. We have everything we need, right? Oh, yeah. So there's our speed. There's our mass. There's the magnitude of the charge. There is b. So let's see what Python gives us. Yeah, so plugging in numbers using Python as my calculator, I get this radius is 0.0954 meters, which you could also say is 9.54 centimeters. Okay, so that's part A of the problem. Then part B of the problem. Now the magnetic field is increased to 1.4 Tesla. What happens to the radius of the path? What happens to the particle's kinetic energy? So I think we can see that the radius is inversely proportional to the magnetic field. So if the magnetic field increases, so we have like the magnetic field new divided by the magnetic field old is 1.4 Tesla divided by 0.350 Tesla. Double that is 0.7, double that again is 1.4. So this is a factor of 4. So we make B larger by a factor of 4, we must make R smaller by a factor of 4. So R becomes smaller by a factor of 4. So in other words, instead of 0.0954 meters, we must have 0.0239 meters. Okay, so the radius of the orbit becomes smaller if we make B bigger. Okay, fair enough. What happens to the kinetic energy? So we know magnetic fields don't do any work. Magnetic fields don't change speeds. It would require an electric field to change the speed. So the speed should be the same, so the kinetic energy should be the same. So we're going to say that the speed is unchanged. Yeah, so we're going to say the speed is unchanged by B, and therefore the KE is unchanged. It's the same as before. Okay. Then there's one more part of this problem. Now an electric field of magnitude 3 times 10 to the 5th volts per meter is applied pointing into the page parallel to the magnetic field. What is the particle's kinetic energy 90 nanoseconds later? And you have to remember nano is 10 to the minus 9. So we want to know. So we have E is 3 times 10 to the 5th. 3.00 times 10 to the 5th volts per meter. Into the page. That's parallel to B. Parallel to B. And then the question is, what is the particle's kinetic energy after t equals 90 nanoseconds. All right. So when we think about that, the particle is going to be, so we're going to add another term here. So usually the way we write this is, we usually do it in the other order. The force, well, this is usually we write the electric force first, but the sum of these two forces is QE plus QV cross B. That's the entire Lorentz force law. So the force electric plus magnetic together is QE plus QV cross B. So the particle is going to be accelerated in the direction of the E field. Actually, it's going to be accelerated in the direction opposite the E field because it is negatively charged. Oh, by the way, a particle whose charge is the same as the charge of the electron, it's negative, and whose mass is the same as the mass of the proton, that must be an anti-proton, by the way. That's kind of interesting. So whoever made up this problem likes anti-protons. So the particle is going to be accelerated in a direction out of the page by the electric field. And then you say, okay, what's the path going to look like? Do I have to know anything else about that? I mean, for instance, is that going to cause some other interaction with the magnetic field, this QV cross B force? So it's going to gain a component of velocity pointing out of the board, since E points into the board. But then that velocity component is parallel, or anti-parallel actually, anti-parallel to the magnetic field, so it's not going to have any effect on the magnetic force. So gaining a velocity component which is parallel to the magnetic field but in the opposite direction is not going to contribute to this QV cross B cross product. So actually what's going to happen is this circle is going to turn into a helix. It'll have the same radius in this plane of the board, but it's also going to be like accelerating out of the plane of the board. So then the kinetic energy can be written like here, K E equals 1/2 mv squared. So we can write that as 1/2 m. Yeah, I didn't define a coordinate system before because I didn't think I needed one, but let's call this the y direction and this the x direction, and then here's the z direction pointing out of the board. So then actually here's vx squared plus vy squared. That's actually going to be unchanged, but then there's vz squared. This is going to be the part that was 0 before when everything was happening in the xy plane, and now we're going to have a non-zero vz. So let's work that out. So the acceleration caused by the magnetic force is just in this xy plane. It's what causes it to continue to go in a circle as projected in the xy plane. And there will never be a z component of the magnetic force here because of this cross product. So the magnetic force is always perpendicular to the magnetic field. So we can work out the acceleration in the z direction. So the z direction is out of the page, and we notice that, by the way, the electric field, now that we have defined a coordinate system, is just this magnitude of the electric field and then it's actually in the minus k hat direction because the electric field, we said, is into the board. So the acceleration, yeah, so basically E in the z direction is minus this magnitude, E. So acceleration in the z direction is going to be q times the z component of the electric field divided by the mass. And this is, well, this is minus okay, so Q is just minus the proton charge. Actually E is the proton charge, you know, like the convention is that you say E is plus 1.602 times 10 to the minus 19 coulombs. So this thing we call little e, where E like kind of stands for electron, is actually the magnitude of the electron charge. It actually equals the proton charge. So here, okay, so the charge seems to be minus E. We don't really care about the sign right here. The charge is minus E. And then the electric field in the z direction seems to be minus this magnitude of the electric field, and then divided by m. So fine. So this is like charge on the proton times magnitude of electric field divided by m is the acceleration in the z direction. So we can use our kinematic equations from the beginning of physics 150. So we'll say the velocity in the z direction after time t is 90 nanoseconds is going to be the acceleration in the z direction times t, because we started out with 0 velocity in the z direction. So that's fine. So then that's just charge magnitude, charge times electric field divided by mass times time. I guess we could put all those numbers together, and that's the only component of, that's the whole velocity in the z direction. The electric field is only changing the z component of velocity, and the magnetic field is just continually mixing up the x and y components of velocity. So this Vx squared plus Vy squared, Vx squared plus Vy squared just equals like this V0 squared from the start of the problem. And then we're going to have this additional Vz. So in the end of the problem, we're going to have the kinetic energy is 1/2 m, and then here's Vx squared plus Vy squared from the start of the problem. So that's that original speed that was entirely in the xy plane initially. So that's V0 squared. And then we're going to get whatever Vz value we calculate here and square that. That's going to be our new kinetic energy. So let's work out these two sets of numbers. Okay, so if you multiply this out, the charge on a proton times the z component of the electric field, that's the only component, times this 90 nanosecond number divided by the mass of a proton. So there's 1.60 times 10 to the minus 19 coulombs. There's 3.00 times 10 to the 5 volts per meter. That's the electric field that's pointing into the page. There's 90 nanoseconds. Remember, a nanosecond is 10 to the minus 9 seconds. So 90 times 10 to the minus 9 seconds. And then divided by the mass of a proton, 1.67 times 10 to the minus 27 kilograms, we get 2.58 times 10 to the 6th meters per second. So that's the velocity component that's going out of the page, actually, toward us. And then now Vx squared plus Vy squared, the part in the xy plane, is unchanged. It's just the square of this initial speed that was given. The kinetic, but then there's an additional velocity component, which is this component out of the plane of the page. So then there's 1/2 mv squared. So this is vx squared plus vy squared, this first term. And then here's this vz that we just calculated, and we square it. So there you go. There's a half, there's the mass, 1.67 10 to the minus 27 kilograms. And then, okay, parentheses. So here's this original V0, we're going to square that. And then here's this VZ we just computed. Put all that together, you get 1.41 10 to the minus 14 joules. So aside from the joy of plugging in numbers, where's the physics? So the magnetic force is always perpendicular to the velocity. As a consequence, it never changes the speed because you need a force parallel to the speed to speed you up. You need a force anti-parallel to the, you need a force parallel to the velocity to make you go faster. You need a force component anti-parallel to the velocity to make you go slower. So the magnetic force just bends you, changes your direction, but not your speed. Then there's the electric force. The electric force does change your speed. Well, another thing about the magnetic force is it's always perpendicular to the magnetic field. So since the magnetic field is in the z direction, or actually the minus z direction, it's not going to produce a force in the z direction. Okay, so then that's nice. It nicely separates the electric and magnetic effects in this problem. So then the electric field is going to produce a force that would be in the same direction as the electric field if the particle were positively charged, but this particle is negatively charged. So the electric field points into the page, so this acceleration due to the electric field points out of the page. So you turn the electric field into a force by multiplying by the charge, and then you turn that force into an acceleration by dividing by the mass. And then we remember our physics 150 kinematics, and we multiply this acceleration component by the time to get, starting from rest, the final velocity component in the z direction. It's starting from rest in that z component. Of course, the x and y components are non-zero, and they're unchanged. Okay, so I think that's kind of interesting, in that you can see the electric field doing work, changing the kinetic energy. The magnetic field doesn't do work, it doesn't change the kinetic energy. And then we're kind of using both terms here, the electric field term and the magnetic field term in the force law. All right, but that was basically, I mean, this problem was not really a tricky problem.